You can see this diagram. I explained you the radio system. Any radio system, you have the modulator, RF converter, then it is coming to the antenna. So normally modulator and RF converter together we call the transmitter. Right? So this is antenna, how it is going. It's a circuit like this. At the end it is open. When it is open, it is going as the electromagnetic wave to the free space. That is how the antenna is working. And the different types of antennas are there: Yagi antenna, parabolic antenna, omnidirectional antenna, like that. So RF converter is a device where you have the analog input is a low frequency analog input. Then it is mixing with a high frequency analog signal, and output will be high frequency analog signal. So we can mix like this the signals, and the high frequency signal is coming out there. So this is called a mixer. So this is your signal. This called carrier signal. These two together mixed, and the output will be high frequency signal. So this is the radiation pattern of a antenna. How the signals are going, right? So signals can be reflected from the ground and also the ionosphere in the sky. So the same signal, when you transmit it is coming to the recipient in many different ways. So the resultant signal, when you add those to the resultant signal, depends on the phase differences of the signal. So if this antenna is moving, the phase differences are moving, and the signal level is fluctuating. So that is called fading. When you see the spectrum of the frequency spectrum, in the free space, the noise is there, different types of noise are there. Therefore, this is the frequency band where normally we can use the frequency band from this 1 gigahertz to about 10 gigahertz. Other frequencies have high noise. So therefore, we are limited. We have constraint to use the frequencies. We cannot use any frequency as we wish for radio transmission. So normally, mobile communication, you use the 1 gigahertz to 2 gigahertz. This is the frequency band used for the mobile communication. And satellite communication, it is 4 to 6 gigahertz. Satellite communication we use 4 to 6 gigahertz, and also some higher, about 10 gigahertz, 12 gigahertz also used. In the wireless communication, we use the 2.4 gigahertz and 5 gigahertz. There are two bands are there. 2.4 gigahertz band and the 5 gigahertz band. Right? So typical radio system, you have the transmitter, then you have the antenna, then the receiver, you have antenna, then you have the receiver. So these frequencies, you have seen the frequency spectrum. This frequency spectrum, we are divided to some ranges, and we are given a name for these ranges. For telegraph transmission or navigation, we use the VLF, very low frequency range. And the sound broadcast to Earth's surface, so it can travel even about 1,500 kilometers. That is low frequency. Then you have the medium frequency, MF, HF, high frequency, that is for commercial radio broadcasting. Then you have the VHF, UHF, that is used for the TV broadcasting. Then the microwave used for the domestic carrier transmission by telcos. Then the satellite communication. So for long distance communication, we can use the satellite communication as well as the submarine cables, that is undersea cables. So I'm not going to touch about the satellite. In the frequency bands, different frequency bands are there. I'll explain those frequency bands. Now in the radio transmission, the signal is going as an electromagnetic wave. So electromagnetic wave is it has electric field, and magnetic field, it is propagation like this. It's a 3D one. So all waves are going as electromagnetic waves. So these frequency bands from 3 to 30 kilohertz is called the VLF, or very low frequency. And 30 kilohertz to 300 kilohertz is called the low frequency, LF. 300 kilohertz to 3000 kilohertz is called the MF, or medium frequency. Then 3 to 30 kilohertz called the high frequency. 30 to 300 kilohertz called the VHF, very high frequency. 300 kilohertz to 3000 kilohertz called the ultra high frequency, or UHF. Then you have the super high frequency, 3 to 30 gigahertz. Then the extra high frequency, 30 to 300 gigahertz. Then the 100 terahertz range is the optical range. In the optical cable, it is going as the optical signal. So that also analog signal, right? Right. Any question from here?
So I have a small doubt.
Yeah.
In a satellite communication, we normally use free space to transmit our signal.
Yeah.
Then, according to my memory, when we have learned when we using satellite communication, we need to direct the antenna towards the satellite. And then why we need to adjust the antenna for that, since it's used a normal open communication medium.
Yes, satellite is moving in an orbit, right? So there is only one orbit called the geostationary orbit, where the orbital time is 24 hours. That means the rotating speed is exactly same to the Earth's rotating speed, right? So therefore then the antenna can be fixed there. You don't have to change the antenna direction, but still the world is not the exact like a globe. So when it is moving in a orbit, there can be a small drifting. So it is not completely synchronized with the Earth rotation. Then we have to slightly adjust the direction of the antenna. Is it clear to your question?
Okay, so then when we using skyline propagation method, we need to adjust our antenna according to that, like this.
Can you repeat?
If we use sky propagation method, if a channel using skyline propagation method to send their signal, then on always we always need to adjust our antenna according to the that symmetry or something.
No, antenna should be always directed to the satellite. If the satellite moves, antenna also move to make the,
okay.
Otherwise the signal is not going to the satellite. Okay.
Okay.
Right. Now we discuss about the transmission media. So transmission media impairments. The problems are noise, attenuation, group delay. So please read this lesson, interference. So it is explained what is attenuation, what is group delay, interference. Now, as a result of this one, when you are sending the digital signal, it can be, actually the digital signal is not transmitted to the free space. It is going as digital signal is converted to analog signal. Then analog signal is going to the free space. In the free space, it is mixing with the noise. The signal can be attenuated. As a result of that, the received digital signal can have errors. Okay. So then we know how to correct errors. For that one, we are using the error correction, error detection and error correction methods. Okay. Any question?
Yeah, if you take there are a lot of HD broadcasting TV channels nowadays, no? So converting their digital signal to analog signal at the transmit, releasing it to free space, and at the reset we are converting again. Is that what happens? So
Can you repeat?
I mean, we have TV channels, HD high definition TV channels now in Sri Lanka as well. So
Yes.
what they actually communicating? Are they communicating? They are communicating to free space anyway. So are they actually releasing a HD signal, or it is just the transmitter?
These signals normally you cannot transmit through free space. Only the analog signals you can transmit. The reason is HD signal reaches a very high bandwidth. So you cannot provide such bandwidth in the free space. Therefore, HD signal should be cable transmission. It should be through a copper cable or fiber. Normally fiber is the best.
But
Okay.
they are saying that they are free to air with HD signals. No, they are advertising like that. No?
They free to air HD signals.
Yeah. In their commercials and all, they say our channel is a high definition channel and it is free to air and all.
Yeah, if they are transmitting the HD signal, still it should be converted to analog signal. Because this whole the whole signals, now they may be given the frequency band in the satellite frequency band, maybe 6 gigahertz. Then they transmit it to 6 gigahertz, it should be converted to analog signal. Even the HD signal, using the codecs, you have to convert it to analog signals. Okay.
So we can use the existing infrastructure like towers and all to transmit. No need of satellite.
Yeah, but the thing is it's not quality when you transmit the HD signals through the free space. Because you have to do a very high compression for that. So it is affected to the quality. But if it is coming through the fiber optic, yes, we are getting the quality. Not only HD, even the 4K you can transmit the fiber optic. 4K, 6K, right?
Maybe
Okay.
up to the
Yeah.
meter.
I didn't hear you, Gopal.
I mean, maybe they are doing something like up to the transmitter, they are getting the digital signal.
Digital signals, yes. Then it will be converted to the analog.
Yeah. Yes,
yeah. But when they are sending through the fiber, they can send the digital signal.
Yeah. That's correct. Yeah.
Right. Then last time I did the bandwidth calculation. The bandwidth is explained here. There's a question this time here about the bandwidth is the transmission media is given. The number of levels were given. No? One MCQ question is there. So you have to use this equation to see what is the bit rate of the signal, maximum bit rate, allowable bit rate of the signal. So if the noise is there, that is assume that there is no noise. If there is noise, so this is the equation we have to see what is the allowable bit rate in the transmission media. Any question? Right. These things you can see from my book also. Then I go to the modulation. I'll explain about the modulation. What is modulation? The modulation is you are modifying the signal. What are you modifying? There are three parameters. We have the amplitude, we have the frequency, and we have the phase. I explained about these three parameters. Now, if you modify the amplitude, it is called amplitude modulation. If you modify the frequency, it is called frequency modulation. If you modify the phase, it is called phase modulation. The sinusoidal signal can be written in from this equation. A sine omega t plus phi. So omega is equal to 2 phi f. Omega is also called the angular velocity, right? So we can convert analog signal to high frequency analog signal using the analog model. Or you can convert to digital signal to analog signal using a digital model. Okay. Is it clear? Any question about the model? Another application of modulation to convert an analog or digital signal to a very high frequency. Analog or digital signal to very high frequency. I told about the RF converter. To convert to high frequency, also you can have the modulator. In the modulator, you have the modulating signal here, input, that is the useful signal. Then the carrier signal, it's a high frequency signal. It's a high frequency signal. Then you mixed up these two, and the output will be the modulated signal, right? So analog signal modulations are called the amplitude modulation, frequency modulation, phase modulation. Amplitude modulation means so this is a useful signal, this is the carrier signal, high frequency signal. This high frequency signals amplitude is changed according to this useful signal, modulating signal. We can see this upper part is say the modulating signal. So this is called envelope. So envelope is equal to the useful signal or the modulating signal. So here you can see the carrier signal's amplitude is changing like this. So that is called AM or amplitude modulation. Then you have the FM, frequency modulation. So this is your modulating signal. This is your carrier signal. The carrier signal's frequency is modified according to the amplitude of the modulating signal. When the amplitude is increasing, frequency is increasing. When the amplitude is decreasing, frequency is decreasing. That is called frequency modulation or FM. Is it clear? In the phase modulation. The phase modulation is a similar manner. You can change the phase. So normally in the analog modulation, we are using the AM and FM. So you know about the AM radios and the FM radios. Any question? Then I have video. I will share that video. It is about the analog modulation and the frequency modulation, AM and FM.
What is amplitude modulation, that is AM? When the amplitude of
Can you see the video?
Yes, sir.
Yes.
Can see, sir.
You can hear. Okay.
high frequency carrier wave is changed in accordance with the intensity of the signal, this process is called amplitude modulation. In the amplitude modulation, only the amplitude of the carrier wave is changed. The frequency and the phase of the carrier wave remains constant. The first visual shows the principle of amplitude modulation. The diagram also shows the audio-electrical signal of frequency Fs. The second visual shows a carrier wave of constant amplitude with frequency Fc. The third visual is the amplitude modulated wave. It is to be noted that the amplitudes of both positive and negative half cycles of carrier waves are changed in accordance with the signal. Thus, the amplitude of the modulated wave possesses the frequency of audio signal waves. Explain frequency modulation, that is FM. When the frequency of carrier wave is changed in accordance with the intensity of the signal, this process is called frequency modulation. In frequency modulation, the amplitude and phase of the carrier wave remains constant. Only the frequency of the carrier wave is changed in accordance with the signal. The frequency variation of the carrier wave depends on the instantaneous amplitude of the signal as shown. When the signal voltage is 0 at A, C, E and G, the carrier frequency is unchanged. When the signal approaches its positive peaks at B and F, the carrier frequency is increased to maximum as shown by closely spaced cycles, but during the negative peak of signal as at D, the carrier frequency.
Okay, I will share this one with you. I'll put it to the course web, you can see it here. Then I will share the book again. This is about the amplitude modulation and the frequency modulation. For the digital modulation, it is called shift key. It is called shift key, amplitude shift key and phase shift, the frequency shift key and the phase shift key. So this is the amplitude shift key. So we can say that if it is 1, amplitude is 0. If it is 2, amplitude is 1. Or you can have the different 2 amplitudes. Now, here 1, 0, 1, 0 is coming. You have 2 different signals. One is high amplitude and the low amplitude. When it is 1 comes, it is high amplitude is coming. When it is low comes, the 0 comes, low amplitude is coming here. So this is the input signal and this is the output signal. So this is called ASK, amplitude shift key. Is it clear that one?
So why it is called shift keying? Is there any?
Yeah, there's a switch. No, the switch is shifting with to one carrier to another carrier depending on whether it is 1 or 0. Shifting is there.
Okay.
Okay. I hope that is clear to you. No? Okay. Now you can see the input is analog digital signal, output is analog signal. Okay. Also, if it is the amplitude 0 is the 0 amplitude, another signal we have with some amplitude, so it is coming like this. If there are 2 signals, it is coming like this. Only one signal and other is 0. 1 and 0 is representing in this way. This is 1, this is 0. Then the frequency shifting, the frequency is changing. There are 2 frequency signals, F1 and F2. So if it is 1, maybe it is going to the high frequency, if it is low frequency, or vice versa. You can see the output signal has this the low frequency and the high frequency. This is called frequency shift key, FSK. Is it clear?
So, 0 voltage means earth voltage?
Yeah, it's a DC current. It's the no voltage. You can't say the earth, it's no voltage. Right? Is it clear?
Yes, I got it.
Okay, phase shift key means the phase is shifting. I explained about the phase. Now in this signal, this is 360 degrees. This is up to here 90 degrees, 180 degrees like that. So if the phase is changing to here, B, it is coming like this, then we call it is 90 degrees phase shifted. If it is starting from C, we call it is 180 degrees phase shifted like this. So this can be represented in a phasor diagram like this. The position A, you can show 0 degrees, it is here. Position B, 90 degrees, it is here. Position C, 180 degrees, it is here. So it is easy to understand by using a phasor diagram. Now signal 1, there are 2 signals. This signal 1 is 0 degrees phase shift, and the signal 2 is here. It is actually there are the two signals with the two amplitudes. Two sinusoidal with two amplitude. So these two signals can be phasor diagram. You can draw like this. In this phasor diagram, the radius is the amplitude. The radius represented the amplitude, and the circle represent the phase. Right? The small amplitude signal in the smaller circle, bigger amplitude signal in the bigger circle. Right? Is it clear? Then the BPSK, bipolar phase shift, means we have only two phases. For 0, it is 0 degree phase shift. 1, it is 190 degrees phase shift. So when it is coming 1, 0, 1, 0, the first one is 0. So there is no phase shift. Second one is 1. It is 180 degrees phase shift. Third one is 0. No phase shift, like that it is going. This is called the bipolar phase shift mean, because there are bi mean there are only two phases. Is it clear? Any question? Then you have the quadrature phase shift key, QPSK or 4PSK. You are taking, you have four phases: 0 degrees, 90 degrees, 180 degrees, 270 degrees phase shift. Right? Now, to represent two phases, you need 2 bits. To represent 4 numbers, you need 2 bits. So therefore, this incoming bit stream is divided to 2 parts. Now this 0 is going to the path P. Next bit is going to the path Q. Then the next one is going to the path P. Next one is going to the path Q. So we are put into 2 parallel stream. Then you take pair of bits from the path P and path Q. Now this is 0, 1. If it is 0, 1, so what will be the phase shift? According to the phasor diagram, it is 90 degrees phase shift. Then your signal will be 90 degrees phase shift. If it is 0, 0, no phase shift. If it is 1, 0, it is 180 degrees phase shift. 1, 1, 270 degrees phase shift. So it is very difficult to show in diagram, but this is how the output signal is coming. That is called the QPSK. Is it clear? Any question?
So what are the devices using this PSK method?
Devices means?
Means normally we use AM, FM for radio broadcasting, like that. PSK for what kind of transmission we are using?
Not transmission. Okay, I'll explain. Here finally you are getting a analog signal output here, right? So as I explained earlier, so you cannot transmit digital signal as a radio wave. First you have to convert it to analog signal. This is the one you are doing. This is the way you are converting your digital signal to analog signal. So this is done from the modulator. So therefore, in your radio system, inside you have a device called the modulator. Modulator is doing this part. Is it clear? Have I answered your question?
Yeah. So basically, when we are using AM or FM, so we can put it to air with the antenna. So in radio broadcasting, we use AM or FM. So in which instance we are using this PSK method? That's what I'm asking.
If it is a digital signal, AM, FM, yes, for the analog signal.
Okay.
So if it is digital signal, first you convert it to analog signal by using this ASK or FSK or PSK.
Okay. Okay.
So we can show mathematically when you go into the more phases, your required bandwidth will be decreased. So if your bit rate is say 100 kilobit per second, if you are using the BPSK, you need half of that one bandwidth, 50 kilohertz. If it is 100 kilobit per second, 50 kilohertz bandwidth is required. So if it is UPSK, the required bandwidth will be reduced to half, because we are getting 2 bit at a time. So therefore, required bandwidth will be reduced. That is the advantage of going to multi-level or the high-level phasers. Similarly, if you go to the 8PSK, you have the 8 phasers, then your required bandwidth will be 1/3 compared to the BPSK signal or the normal signal, the signals. So you can have the hybrid modulation, that is the ASK and FSK together, that is called the quadrature amplitude modulation. This is called QAM or quadrature amplitude modulation. So nowadays, the radio systems are using 64 QAM, even the 256 QAM are using. Advantage of that is the required bandwidth will be reduced. The transmission media required bandwidth will be less. So we can go to the 64 QAM, then the 256 QAM like that. Right? So that is the modulation, digital modulation. Any question? Question asked, should a phaser diagram always complete the circle? Can it stop and half circle? So it is, if you represent a one cycle, it will be one circle. If you represent half cycle, it is the half circle. Okay. I think I answered your question. If it is 720 degrees, that is, if it is 2 cycles, it will be 720 degrees, then the 2 circles, right? Is it? Did I answer? That is Dimalsha. Dimalsha Tatsar. Is it clear to you?
Yes, sir.
Okay, another question asked, what is the difference between radio wave and microwave? Microwave is some kind of radio wave, right? It's a amplitude is micro, small. That's why the word micro is used. Right?
So what is the 1, 0, 11, 10 numbers calculation?
This one.
Yeah.
This is 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0 means the 0 degrees phase shift. 0, 1 means the 90 degrees phase shift. 1, 0 means the 180 degrees phase shift, and 1, 1 will be the 270 degrees phase shift. Okay. Then I have a video, I will share that one. Okay. This video about the ASK, FSK, and the PSK.
I think we should explore a few solutions.
Grammarly ensures your writing conveys.
Hello, and this is Sunny. Welcome back. Last time we talked about 2 analog modulation methods, AM and FM. Today we will talk about 3 types of digital keying. Before we get into these 3 digital modulation methods, let's quickly review a wave's amplitude, frequency, and phase. A wave has a highest point called crest, and in other words, the greater a wave cycle passes the line point within a wave cycle. The locations on a wave cycle can be specified as an angle in either radians or degrees, as well as in fractions of a cycle. This can be visualized with a rotating wheel and a spoke tracing the wave as time goes. Now let's see how each detail modulation.
Okay, this also I will share with you. Then you can watch it later. Then I have a very good video about the antenna, how the antenna is working. I will share that one with you.
The shape and size of an antenna is a function of its purpose. But whatever its physical form, it is designed to transmit and receive electromagnetic waves. Let us first consider a hypothetical antenna, the point source. From such a source, energy radiates outwards in all directions. Let us examine this process more closely. The radiated energy can be represented by a traveling waveform of this shape. The waveform normally follows a sine curve. We will consider one complete cycle of the wave. It is defined as one wavelength. We can relate the wavelength of the radiation to the antenna which produced it. An antenna which accommodates half a wavelength is the simple dipole.
You can see this one, no? You can hear.
Yes, sir.
Okay, this is very interesting one.
If we feed a signal to this antenna, an electron flow will be set up within it. The electron flow first produces a maximum concentration in this direction, reverses, then produces a maximum in the opposite direction. Flow reverses, maximum. This cycle repeats itself at the signal frequency. This electron flow creates a fluctuating magnetic field. Let us relate the direction of this field to the electron flow. As the electron flow reverses, the magnetic field is at a maximum, and the lines of force are in this direction. When the flow stops, the lines of force collapse. As the flow reverses, the field again reaches a maximum. The lines of force are now in the opposite direction. The magnetic field thus reverses its direction at each half cycle of the signal frequency. This is known as the H field. The strength of this field is proportional to the amplitude of the current standing wave.
So this is the magnetic field. So electromagnetic field have electric field and the magnetic field.
This current standing wave is 90 degrees out of phase with the voltage standing wave. At this instant, the antenna has a positive voltage at this end. When the polarity reverses, notice that the lines are at right angles to each other, plane of the E field. To obtain a maximum signal, both the transmitting and receiving antennas must be in the plane of the E field.
Okay, you can. I will share that also with you. So that will give about the antenna theories. So today we have done mainly the modulation and the antenna, and I explained about when you want to send a signal, we need if it is a voice signal, we need the microphone to convert to electrical signal. From the codec, it is converted to digital signal. Then to have the radio transmission, this digital signal should be again converted to analog signal. For that one, you need the modulator. Then it should be converted to high frequency signal. So that is called RF converter. RF converter also is a special modulator, shared modulating signal and the carrier signal, high frequency carrier signal. Then the output will be the high frequency signal. Finally, it is coming to the microphone. Sorry, it is coming to the antenna. From the antenna, it is coming to the free space. So those are the things we discussed. If you have a question, you can ask me now.
Sir, what is the maximum amount of a frequency that's going from a electric terminal in Sri Lanka?
Maximum what?
Maximum number of kilometers the signal goes in Sri Lanka in electric poles?
Electromagnetic waves.
No, electricity terminals, in electricity terminals.
Electricity, they can transmit any distance. But if it is
10,000 kilometers. I want to know the maximum amount.
If you are going to more and more distance, then you need the more higher and higher voltage. If it is lesser distance, 33 kV. If it is going to longer distance, 132 kV. Then if it is more than that, 230 kV. Then if it is very long distance, 400 kV like that. But in Sri Lanka, you have only the 132 kV. We don't have very much long distances.
So only 130, right?
132. Okay.
Okay.
Okay. Any other question?
So in Sri Lanka for mobile communication, do we use radio waves or microwaves?
That term you don't have to worry much, because those are the waves given to the frequency bands, right? So I showed you the frequency bands. No, what is microwave? Microwave normally it's called to, I think, the 1 to 10 gigahertz. So this mobile communications come between 1 gigahertz and 2 gigahertz. Mobile communication frequencies are between 1 gigahertz and 2 gigahertz. Okay.
Okay.
So it can be 1900 megahertz, maybe the 2100 megahertz, like that. Right?
Okay.
Any other question? Okay. Yeah.
Can you,
Yes.
you describe what that video shows about that antenna producing signal?
Yes.
Can you briefly describe what actually is happening there? I don't understand.
I will share this video. It explained very well.
Uh-huh.
What is a current? Current is electric field, electron movement, right? When the
Yes.
electron movement, there is a current. When there is a current, there is a surrounding magnetic field, right? You
Yes.
studied in the physics these things. That is the one it is using. They are changing the current direction, then the magnetic field direction also changing. So that is the way they are producing the electromagnetic wave. Is it
Actually,
clear?
I was for A level, so I don't know about physics, but it showed the antenna that there is an energy flowing from left hand side to the right hand side.
Yes.
How that happens? Is it the level of the signal, amplitude of the signal?
Which one? Amplitude of the signal depends on the current. How much current is flowing there. Because the energy depends on the amplitude.
Okay.
Okay.
Okay. I'll watch it as well.
Yeah. This might be very interesting to you. These are practical things. Any other question you have?
What is the maximum voltage of the CEB?
132 kV.
Okay, okay.
Okay.